So far, we talked about how to determine if one-dimensional function is convex, concave, or indefinite by using the second derivative. If we have a function with multi-variables, then how can we determine the convexity and the concavity of this multi-variable function? As this function has multiple variables, we usually use a lowercase upright boldface x to denote a vector of variables. If we see such kind of x, then it means this function has multiple variables. We first introduce the Hessian matrix of a multivariable function. This Hessian matrix is a matrix of the second partial derivatives with respect to each variable for a multivariable function. If we have a multivariable function f(x), in this function f(x) we have n variables. Which are denoted as x1, x2, x3, and xn. To get the Hessian matrix, we first need to calculate the partial derivatives with respect to each variable x. For instance, we calculate the partial derivative with respect to x1. We also calculate the partial derivative with respect to x2 until we also calculate the partial derivative of f(x) with respect to xn. Then we can get a vector of the partial derivatives. This vector is also the gradient of function f(x). Based on the partial derivatives of f(x), we can construct the Hessian matrix. As we have n variables, this matrix is a n times n matrix. That means this Hessian matrix has n rows and n columns. It is a square matrix. Let's use I to denote rows, J to denote columns of this Hessian matrix. Then the entry in the ith row and the jth column of this Hessian matrix is equal to the second partial derivative of function f(x) with respect to xj first and then xi. When I is equal to 1, j is equal to 2, then we can get the entry in the first row and the second column of this matrix. That is the second partial derivative of f(x) with respect to x2 first and then x1. When I is equal to n, j is equal to n, then we can get the entry in the nth row and the nth column of this matrix. That is the second partial derivative of f(x) with respect to xn first and then xn, which is the same as this term. There is one important property of this matrix, that is, this Hessian matrix is always symmetric. This is because the second partial derivative of fx with respect to xj first and then xi is equal to the second partial derivative of this function fx with respect to xi first and then xj. That means the transpose of this Hessian matrix is equal to the Hessian matrix itself. It is very important to know the Hessian matrix is always symmetric. Please remember this point. We usually use an uppercase, upright, boldface H to denote the Hessian matrix. We also need to know some definitions related to this Hessian matrix. A Hessian matrix is positive semi-definite if and only if this condition, this inequality constraint, is satisfied for all x is not equal to 0. That means if a Hessian matrix is positive semi-definite, then we have this condition. We have this inequality constraint for all x is not equal to 0. If this inequality constraint is satisfied for all x is not equal to 0, then this Hessian matrix is positive semi-definite. A Hessian matrix is negative semi-definite if and only if this inequality is satisfied for all x is not equal to 0. That means if a Hessian matrix is negative semi-definite, then this inequality constraint is satisfied for all x is not equal to 0. Alternatively, if this inequality constraint is satisfied for all x is not equal to 0, then this Hessian matrix is negative semi-definite. Similarly, we can also use these two conditions to determine if a Hessian matrix is positive definite or if this Hessian matrix is negative definite. If this term is negative for some x and positive for other x, then this Hessian matrix is indefinite. These are definitions of positive semi-definite, negative semi-definite, positive definite, negative definite, and indefinite of a Hessian matrix. In these definitions, we have this term X transpose times the Hessian matrix times X. This term is a scalar. This is because X is a vector of variables, which is usually denoted as a column vector. If we have n variables, then the vector X is a n times 1 matrix. X transpose is a 1 times n matrix. So then X transpose times the Hessian matrix H times X is equal to 1 times n matrix times n times n matrix. This is because the Hessian matrix is n times n square matrix times n times 1 matrix. Then we can get this term is equal to 1 times 1 matrix. That means this term X transpose times the Hessian matrix H times X is a scalar. Now we can present the necessary and sufficient conditions that can be used to determine if a multivariable function is convex or concave. In these necessary and sufficient conditions, we use the Hessian matrix of this multivariable function. We have a multivariable function fx. If the Hessian matrix of this function fx is negative semi-definite, then this function is concave. If the function fx is concave, then the Hessian matrix is negative semi-definite. If the Hessian matrix is negative definite, then this function fx is strictly concave. The reverse is also true. If the Hessian matrix is positive semi-definite, then this function is convex. If the function fx is convex, then the Hessian matrix is positive semi-definite. If the Hessian matrix is positive definite, then this function fx is strictly convex. The reverse is also true. That is, if the function fx is strictly convex, then the Hessian matrix is positive definite. If the Hessian matrix is indefinite, then this function fx is neither convex nor concave. The reverse is also true. That is, if a function fx is neither convex nor concave, then the Hessian matrix is indefinite. Now the question is, how can we determine if the Hessian matrix is negative semi-definite, negative definite, positive definite, or positive semi-definite? Of course, we can use these definitions. That means we need to calculate the value of X transpose times the Hessian matrix and times X, and then to determine if this term is positive or negative, then we can determine if the Hessian matrix is positive semi-definite, negative semi-definite, positive definite, negative definite, or indefinite. However, using these definitions is not convenient in most cases. This is because we need to prove if the term X transpose times the Hessian matrix times X is positive or negative for any X which is not equal to 0. There is one convenient way that can be used to determine if the Hessian matrix is positive semi-definite or positive definite. In this approach, we use eigenvalues of the Hessian matrix. That is, if all the eigenvalues of the Hessian matrix are non-negative, that is, all eigenvalues are greater than or equal to 0, then this Hessian matrix is positive semi-definite. As we discussed previously, if the Hessian matrix is positive semi-definite, then we know the function fx is convex. If all the eigenvalues of the Hessian matrix are positive, that means all eigenvalues are greater than 0, then the Hessian matrix is positive definite. As we discussed previously, if the Hessian matrix is positive definite, then this function fx is strictly convex. Then we need to determine the eigenvalues of the Hessian matrix. How can we determine the eigenvalues? Let's use lambda to denote the eigenvalues of the Hessian matrix. We first calculate a matrix that is the Hessian matrix minus lambda times the identity matrix. Then we calculate the determinant of this matrix and let the determinant of this matrix is equal to 0. Then we can get the value of lambda. Based on this, we can determine the eigenvalues of the Hessian matrix. If the Hessian matrix is n times n matrix, then we can get n eigenvalues. Some eigenvalues may be the same, but we should obtain n eigenvalues. Let's look at example 1. In example 1, we want to determine the convexity of this function fx. In this function, we have two variables, x1 and x2. If we want to determine the convexity of this function, we first need to obtain the Hessian matrix of this function. We first get the partial derivatives with respect to each variable. We calculate the partial derivative of fx with respect to x1. Then we get this one. We also need to calculate the partial derivative of fx with respect to x2. Then we get this one. Using these two partial derivatives, we can calculate the second partial derivatives with respect to each x. The second partial derivative of fx with respect to x1 is equal to 4. The second partial derivative with respect to x2 is also equal to 4. And the second partial derivative with respect to x1 and x2, or x2 and x1, both are the same, is equal to minus 3. Then we can obtain the Hessian matrix of this function fx. Now we want to determine the status of the Hessian matrix. First, let's use the definitions. That is, we need to calculate the term x transpose times the Hessian matrix H times x. As we mentioned previously, in this term, x is a vector. We need to prove this term is positive or negative for any vector x which is not equal to 0. This x is any vector which is different from the variable x in the function fx. To differentiate the vector in the term from the variable in the function fx, we use vector y instead of x in the term. That is, y transpose times h times y, this term. Let's define this vector y, which has two elements, y1 and y2. This is because the Hessian matrix is a 2 times 2 matrix. Now we can calculate the value of y transpose times h times y, that is equal to this one. As we mentioned previously, this term is a scalar, so then we can get the value for this term. By arranging this term, then we can get this one. As the vector y is not equal to 0, that means y1 and y2 are not equal to 0 at the same time. Then this term is always positive. In other words, this term is always greater than 0. From the definitions, we can conclude the Hessian matrix Hx is positive definite. So then we can know the function fx is strictly convex. For this example, it is not too difficult to prove the term y transpose times the Hessian matrix times y is always positive. However, if the Hessian matrix is a bit more complicated, let's say if the Hessian matrix is a 4 times 4 matrix, then it is not convenient to prove. Okay, let's use the eigenvalues. We first need to determine the eigenvalues of this Hessian matrix. We let lambda to denote the eigenvalues of the Hessian matrix. We first calculate a matrix, which is the Hessian matrix minus lambda times the identity matrix. Then we can get this matrix. Next, we need to calculate the determinant of this matrix and let the determinant be equal to 0. Then we can get an equation related to lambda. By arranging this equation, we can get this equation. After we solve this equation, we can get the eigenvalues of this Hessian matrix. We can get two eigenvalues. This is because the Hessian matrix is a 2 times 2 matrix. The value of the first eigenvalue is equal to 1. The value of the second eigenvalue is equal to 7. Both are positive. That means the Hessian matrix is a positive definite. Then we can conclude the function fx is strictly convex. You can compare these two methods, and then you will see using eigenvalues to determine the status of the Hessian matrix is more convenient. This is why we usually use the eigenvalues to determine if a Hessian matrix is positive definite, positive semi-definite, negative semi-definite, negative definite, and indefinite. Let's look at example 2. In this example 2, we want to determine the convexity of this function fx. This function is a bit more complicated than the function in example 1. First, we also need to obtain the Hessian matrix. We first calculate the partial derivative of fx with respect to each variable. That is, the partial derivative with respect to x1 is equal to 4 times x1 plus 2x2 plus 7. We can also calculate the partial derivative of fx with respect to x2, that is 2x1 plus 3x2 plus 8. Now we can calculate the second partial derivative of fx with respect to x1, that should be 4. And the second partial derivative with respect to x2 is equal to 3. We can also calculate the second partial derivative with respect to x1, x2, or x2 and x1. They are the same. Then we can get the value is equal to 2. Then we can obtain the Hessian matrix of function fx. Let's obtain the eigenvalues of this Hessian matrix. To determine eigenvalues of the Hessian matrix, we need to obtain this matrix. Here, lambda is the eigenvalues. Then we obtain this matrix. We need to calculate the determinant of this matrix. That should be this one, 4 minus lambda times 3 minus lambda minus 2 times 2. And we let this determinant is equal to 0. Then we get this one. After arrangement, then we can get this one. Lambda square minus 7 lambda plus 8 is equal to 0. Solving this equation, we can get the values of the eigenvalues lambda 1 and lambda 2. Lambda 1 is equal to 5.56. Lambda 2 is equal to 1.44. Both are positive. Then we can confirm this Hessian matrix is positive definite. Then the function fx is strictly convex.